This is a selective precipitation question, and there's a lot going on, so let's take a minute and look at physically what's in the beaker. We have 7 cations that are present, and they all are at the same concentration, 0.010 molar. We also have the solution buffered so that H3O plus ion concentration is 0.3, and we have generated H2S gas in situ so that it's saturated, and that corresponds to a concentration of 0.10 molar H2S gas. And for such a situation, the equilibrium constant that's associated is the KSPA. This is a dependent equilibria of 3 different equilibria, and that's why we get the KSPA. It's going to be equal to the metal cation concentration times H2S divided by H3O plus quantity squared. Alright, so all of this is in the beaker. Now we look up at the question stem, and it asks us which of these 7 cations will precipitate as a sulfide. So for any precipitation to occur, we know that IP has to be greater than KSP. So IP has to be greater than KSPA. So let's calculate what IP of this situation is. It's going to have the same form as K, but we are determining whether or not we're at equilibrium. So it's the same form as KSPA, so we have our metal cation concentration of our H2S that's dissolved in the solution, and H3O plus ion concentration squared. We can substitute in the values that were given. And we get a KSPA or QSPA, an IP value that's equal to 0.011. Alright, now for precipitation to occur, IP has to be greater than KSPA. So we get our IP, and we're going to compare it to the KSPA of our given ions. And you may note that these are kind of grouped in 2 separate groups. The reason being that these correspond to our group 3 cations from lab. Okay, group 3 are the base insoluble sulfides, and they have KSPA values that are considerably larger than those of the acid insoluble sulfides. These are the group 2 ions. These are the acid insoluble sulfides. And we see why right now, because all of these acid insoluble sulfides, we are in acid solution. When we calculate our IP, all of these acid insoluble sulfides are going to precipitate as the sulfate. So we're going to precipitate HGS, copper sulfide, and lead 2 sulfide. Okay, so their IP is greater than the KSPA. However, these group 3, the base insoluble sulfides, are going to remain in solution. because the IP is smaller than their KSPA values. So their KSPA values are larger than the ion product that exists at in this particular situation. Alright, so the second part of this question is, what pH is needed to precipitate all 7 of these cations as a sulfide? So we want to precipitate all of these. We need the IP to be greater than KSPA. Alright, so if we look at our group 3 ions, we see the one that's the most soluble sulfide out of all of these is the manganese sulfide. So if we can generate conditions where manganese sulfide is going to precipitate, we know that all of the rest are going to precipitate. Alright, so we need to find conditions in which, let's start by finding the equilibrium condition. For our manganese sulfide. Okay, so we would have KSPA has to be equal to M2 plus times H2S divided by H3O plus quantity squared. Okay, so what we want to find is what H3O plus ion concentration is required for this to equal 3 times 10 to the 10th. Alright, so H3O plus quantity squared is going to be equal to M2 plus H2S divided by our KSPA, which is 3 times 10. Let's just write KSPA, then we'll substitute values. KSPA. Alright, so let's substitute our values. Our metal ion concentration is 0.010. H2S 0.10, and our KSPA is 3 times 10 to the 10th. Alright, what we want to calculate is not H3O plus squared, but H3O plus. So we want to take the square root of everything so that we can find H3O plus. Alright, so we multiply this out. This times this divided by our KSPA, take the square root. We find that H3O plus ion concentration at equilibrium is 1.83 times 10 minus 7. Alright, so now we need to think about what we're going to do with this value. This is the concentration of H3O plus ion at which manganese sulfide is at equilibrium. We want it to precipitate. So let's remind ourselves, IP has to be greater than KSPA for this to precipitate. So our IP has to be greater than our M2 plus H2S and H3O plus ion concentration squared. Now, for this to be true, what has to be true about H3O plus ion concentration? Now, these values are set. These are constant. They're not going to change. We found that for IP is going to be equal to KSPA, when H3O plus ion concentration is equal to this value here, 1.8 times 10 to the minus 7. By the way, we can only have one sig fig there. Alright, so in order for IP to be greater, H3O plus ion concentration, since it's in the denominator, has to be smaller than 1.8 times 10 to the minus 7. Okay, so it's going to have to be more basic than 1.8 times 10 to the minus 7. Okay, the pH that corresponds to this concentration is equal to 6.74. So in order for all of these to precipitate, we need to have a pH that's more basic than 6.74, and that's why pH has to be greater than 6.7, for which we have one sig fig in our answer. So again, we want IP to be greater than KSPA. Since H3O plus ion concentration is on the denominator, it needs to be smaller than the concentration at equilibrium. Here's our equilibrium concentration. H3O plus ion has to be smaller than this value, so it has to be more basic, and therefore the pH has to be more basic than 6.7.